Good day, ladies and gentlemen. This is the pre-prac video for experiment 5, the quantum mechanical and spectrophotometric study of methyl red. So in this experiment, firstly, you are going to determine the pKa of methyl red using spectroscopy, specifically UV spectroscopy, and you're going to apply the 1D particle in a box model to this molecule to determine its absorption frequency nu. Okay, as you know, methyl red is commonly used as an indicator, and the reason why we can use it as an indicator is because it has different colors in acidic and basic solution. So it has an acid form and a basic form. So in an acidic solution, the methyl red molecule is protonated, and we indicate that with that hydrogen. So we're going to use that abbreviation for the protonated form, and in basic solution it is deprotonated. The acidic form is red, the basic form is yellow, which is of course why we use it as an indicator, because it has different colors. This form, the acid form, absorbs at 520 nanometers, the basic form at 225 nanometers. Both of these fall in the UV range. Okay, so in this experiment you are going to prepare a number of solutions. To save yourself some time, do the calculations at home beforehand and just check your calculations with your demi, because you're going to prepare a lot of solutions. If you do your calculations incorrectly, you are going to have to repeat the preparation of the solutions, and this will waste a lot of time. In addition to that, you have to work analytically. Every drop counts. So use pipettes and volumetric flasks to prepare these solutions. So the preparations of the solutions are described in your practical manual. You're going to prepare a standard solution and a solution A and solution B. Solution A is an acidic solution, solution B is a basic solution, and from these you are going to prepare a range of dilutions. So when you dilute solution A, you're going to prepare a range of acidic solutions, from solution B a range of basic solutions. So if we summarize that, we're going to have a set of acidic solutions, so dilutions, different dilutions. We're going to have a set of basic solutions. So these will be prepared from solution A, from solution B, your basic solutions, and then in addition to that you will also prepare some unknown solutions. These are your mixtures number 1 to 4. So that is your third set of solutions, your unknowns. So that would be 1 to 4. Okay, so your acidic solutions obviously contain the acid form of methyl red, because it's an acid, so those contain MrH. Your basic form would be Mr- in the basic solutions, and your unknowns are chosen in such a way as to contain both MrH and Mr-. Your acidic form, so for these solutions, these dilutions, you're going to measure at 520 nanometers. Basic form, you're going to measure at 425 nanometers. Since your unknowns contain both forms, you're going to measure these at both wavelengths, at 520 nanometers and 425 nanometers. You're also going to measure the pH of your unknowns. So once you have done that, you're going to use the results of these two measurements of your solutions made from A and B to construct calibration graphs. So you're going to have a acid calibration graph and a basic calibration graph. So this is basically a calibration graph for your MRH form, a calibration graph for your MR minus form. So in this you're going to have your different dilutions. So for your different solutions concentration, you plot absorbance, and the same for your basic form concentration, absorbance. So these give you, so these solutions you just use to construct the calibration graphs. You then use these calibration graphs to determine the concentration of these two species in your unknowns. So for example, in, let's say, unknown solution 1, you will measure absorbance at 520 nanometers, absorbance at 425 nanometers, and of course you will have a pH for solution 1, and you'll do the same for solutions 2 to 4. You use your absorbance for that specific solution at 520, and you go to your calibration graph at 520. For that specific absorbance, you can now get the concentration of MRH in your first unknown. So from that, you get the MRH concentration. You do the same for MR minus. You've got the absorbance at 425. Let's say it's that value. You can measure, read off the concentration of MR minus from the calibration graph for your first unknown solution, and you also have the pH for that unknown solution. You then use this information to calculate the pKa for unknown solution 1, and you do the same for unknown solutions 2 to 4. Now in order to do that, you will use the following equation. Which you will find in your practical manual. So for solution 1, unknown, you have pH, you measured that. You have MR minus concentration, which you measured off the calibration graph or read off the calibration graph, and you have MRH concentration. From that, you get the pKa from solution 1. You do the same thing for solution 2, for solution 3, and for solution 4. You can then get an average pKa for the 4 solutions. And remember, it's always good practice to then compare that experimental pKa that you got with the literature value of the pKa for methyl red. Remember to always give the reference for where you found that literature value that you referred to. Okay, so that is the first part of the experiment or the interpretation of the results. I just want to refer you to the questions in the practical manual. So if you look at questions 4, 5 and 6, 4 asks you to draw graphs of the experimental absorbency versus concentration at 425 for your basic solutions and 420 for your acidic solution. So that is basically constructing these two calibration graphs. So that is question 4 in the manual. Question 5 tells you, use the absorption values obtained for the mixtures to determine the MRH and MR minus concentrations from the graphs, and then put these in tables. So that is basically when you use these unknown absorptions that you've measured and you read off the concentrations there. So that is that step for solutions 1 to 4. So doing this would be question 5, and of course the reading off. And then question 6, calculate the pKa of methyl red, which is what I explained here. Okay, and then the second part has to do with applying the particle in a box model to this molecule. So that involves question 1, 2 and 3. So we assume that this molecule can be seen as a particle in a box, particle in a one-dimensional box. And we have electrons in this box, and we can use this information and the application of the model to calculate the absorption frequency of this molecule. Because remember, you measure absorbance using UV spectroscopy. So what we need is the length of this box, which we indicate with symbol uppercase L. If you look at your practical manual, on the first page you are shown a drawing of the methyl red molecule, and it also tells you that you can calculate the length of the molecule of this pi system as the sum of the bond lengths between the two marked atoms on this page. So the first atom is this oxygen atom, and the last atom is this carbon atom. So the length of the box you consider to be starting at that oxygen atom, carbon, along the shortest path until you reach that carbon atom. And then you are given the different bond lengths for the different bonds involved in this molecule. So that is how you get the L value. So you can calculate the length of the box in this molecule. Second part of the question, or it's also related to the first part, asks you to calculate the energy levels. So in the manual you'll find this equation. L is of course the length of the box that you've just calculated, and M is the mass of an electron, which you'll find in your data sheet. N is the quantum number for the particle in a box. It starts from 1 going to infinity. And specifically the question asks you to calculate the energy levels for N equal to, N starting at 1 going to 7. So you can calculate the values E1, E2, E3, E4, E5, E6 and E7 by changing N from 1 to 7. H is Planck's constant, you've got the mass, you've got the length, so you can calculate En. Second part of the question, or second question, represent the energy levels graphically. So here you have to take the spacing into account and also the values. So I'm just going to make a rough drawing. Obviously this is not to scale. So you will have E1, E2, E3, 4, 5, 6, 7, and I'm running out of space. Okay, so obviously the spacing is not correct, but you can check that, or you can correct that. And then they ask you to calculate, so that's representing it graphically, calculate the absorption frequency, so that's nu, for MRH and MR minus. Assume MRH contributes 10 electrons. So let's look at that one first. So it is a conjugated system. So for MRH, we have 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when it absorbs, an electron will go from the highest filled level, which is E5, to the highest the highest unoccupied level, which is E6. So my delta E is E6 minus E5, which would be H nu. Energy that you calculate here will be in joule, but remember you want frequency, so you can just convert that to frequency using that difference in energy. And then of course these frequencies that you've calculated for MRH, you can do the same thing for MR minus. You can then compare to the values that we've given you, namely MRH, we said it's 520 nanometers, so just convert the frequency to wavelength, and this one 428 nanometers, or convert these wavelengths to frequencies and compare. Okay, so that is in a nutshell what this experiment is about.